Hey guys, so this is the next trend after atomic radius. This is going to be ionic radius. A couple things you need to know about ionic radius. First of all, we need to put some context to this. So we should know that atoms in the natural state should have an oxidation number of 0, right? As they're all natural and neutral. When it's bonding, though, we should expect to know also what oxidation numbers they have. So, you know, for example, oxygen will always have a -2, chlorine will always be a -1, helium will be 0 because it's always a noble gas and won't bond. Now the ionic radius then is the radius of the ion when it has the oxidation state that you expect. So it's not just any old ion, it's going to be the actual oxidation number that you expect it to form. Two parts of the trend we want to consider. The first one is going to be the ion versus the atom size for a single element. So say for example lithium versus lithium plus 1. Or the other one is going to be an ion versus ion, and this is comparing different elements. So this is more like the other trend where you're moving left across the periodic table. What does it change? Going top to bottom, what's it change? So on and so forth. And we'll be using effective nuclear charge to help us explain a lot of these. Let's go and take a look at the first one. Let's say we have a cation. Remember, these are going to be your positive ions here. We're using magnesium. Magnesium has 12 protons, 12 electrons to assign. So let's go ahead and assign those 12 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11, 12. Now, most of you should also know that magnesium, when it forms an ion, is going to become magnesium 2+. And we've discussed this before. The two electrons it's going to lose are these two outer ones, so these go away. And what you're left with then is just these right here. So 1, 2, 3, 4, 5, 6, 7, and 8, 9, 10. Okay, now, so based on this, you should be able to predict, in terms of which one's going to be bigger or smaller, that your cation will actually end up being smaller. Right? This is going to be smaller than this one. So the size decreases when you see magnesium become an ion. Now, why is that? There's two reasons. I want to make sure you guys understand that both these reasons are important. The first reason should be a little bit more obvious, at least from this visual perspective. So you have 2 electrons that go away. So that means you have no more electrons in this third energy level. That means the only electrons are in the lower energy levels. That means these right here. So physically, again, you're going to have lower energy levels because the outermost energy level is now empty and devoid of electrons. So that makes it smaller. Additionally, the second reason is that this right here, if you notice, you have 10 electrons now, but you have the same number of protons, so that hasn't changed. So that means your effective nuclear charge has remained the same, but the number of electrons that are there has decreased. So your effective nuclear charge is now distributed amongst fewer electrons. Therefore, it allows the pool of the protons to bring in those electrons in tighter. So again, there's a twofold reason here. Whenever you lose electrons, valence electrons, you end up losing all the outermost electrons, so you're only left with the inner electrons, and that's making it smaller. But also, you end up losing, you end up having a more concentrated effective nuclear charge on the remaining electrons, pulling them in tighter. On the opposite side, you have sulfur. Sulfur has a lot more electrons, has about 16 that you want to assign. So it goes 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. And then you have 6 more out here. Right. So as a comparison, of course, sulfur is going to form an anion because it's going to reach octet stability by gaining 2 electrons. So over here you're going to have it as a -2. And of course, to make it -2, you're going to end up adding 2 electrons. So if I can redraw these again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 1, 2, 3, 4, 5, 6, 7, 8. That demonstrates that you have your octet rule satisfied. So you're going to have a stable -2 ion. But if you take a look at it, again, what happens to my size? Well, since you add electrons to your outermost ring, you're not really adding it to another ring, like you're not adding to the force. That's not a factor. But you are, again, increasing the number of electrons. So the effective nuclear charge that's in here is distributed amongst more electrons, and that again allows it to expand. Also, something else you want to consider is that you've added more negative electrons to a closer area. So in reality, you have another reason, is that the repulsion of these electrons against each other will increase, therefore forcing them to sort of push away from each other. So again, this also has a twofold explanation. Not only do you have the repulsion from additional electrons, but you also have the additional electrons that is spreading out the positive charge more thinly. Now, This is again comparing it from different elements. So before we just saw an atom change to an ion. This time we're taking ions of different elements and then making sure that you have a decent comparison. So the gray for these typically is your pure element, so the neutral one that has no charge, and the colored one, whether it be pink or blue, is your ion. Now you kind of notice a trend here as you go from left to right. It sort of gets smaller and smaller and smaller, and then over here notice it gets big again, but then it gets smaller. So this one again gets smaller, 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 big again, then gets smaller, and this trend happens upon every period. And that's actually explainable. We'll come to that in just a moment. But going down, it gets bigger. So going left to right decreases. Going from top to bottom, it increases. And so that basically reflects the same pattern as your atomic radius. Now, one thing I also want to mention here is that, again, this little split right here where you see a kind of a jump, so you kind of get smaller, but then all of a sudden there's a jump to get a bigger ion. What's up with that? So why is my ion, again, getting smaller and smaller and smaller, and then right here it gets bigger? Well, actually the jump happens between the carbon group and the nitrogen group, which actually aren't demonstrated on this diagram right here. That's fine. So you can kind of imagine I'm talking about the carbon elements, the carbon group down here, and then the nitrogen group underneath that as well. Well, what's going on? Well, remember that everything from the left over up until this point, including the carbon, all those to get the actual, octet rule to make sure their outermost energy level is satisfied, they all gain electrons. So they all lose electrons. Sorry, they all lose electrons. So all these again lose electrons. As we saw from the previous slide, that means you get smaller and smaller as you lose electrons as you go from left to right. Also, the effective nuclear charge is increasing. But from the right, from nitrogen onto the right, they're all gaining electrons. So all these are negative. And as such, when you go across that little boundary right here, across this junction, you end up having to add electrons. You end up adding 3 electrons. It's actually quite significant. So you end up getting a big jump going from a carbon ion to a nitrogen ion. Oh, by the way, this is a very common question that I've seen, and people like to see this too. So make sure you guys understand how that works. Moving on, isoelectronic. This is a pretty straightforward concept. Iso meaning the same, obviously, and electronic refers to the electron. So this is basically saying species that have the same number of electrons but have different elements. Right? So now in this case, I have the example of chlorine ion, argon, and potassium ion. So it should make sense to go through these. If I count out how many protons, it would go from 17 protons to 18 protons to 19 protons. Right? So that's pretty easy to count. But I'm asking for the number of electrons. Well, in terms of electrons, this will have 18 electrons, this will have 18 electrons, and this will also have 18 electrons. So it should make sense. All of them have the same number of electrons, but differing numbers of protons. Now, logically, which one then would be the smallest or largest? Well, since you have the least number of protons here, and this one has the most number of protons, this has much more pulling power than this one does. So that means this one's going to be pulling in their electrons much more than your chlorine. Therefore, this one will be the smallest. So the order in which this would go would be K plus first, then your argon, and then your chloride ion, which would be the largest. Ionization energy, next trend here. Ionization energy has a fairly complex definition, but it's not one that you necessarily have to spend a lot of time memorizing. Essentially, again, it's the energy input required to remove the ground state electron, I think I left that word out, ground state electron, of your isolated gaseous atom or ion. So removing electrons here. And typically it's going to be your valence or outermost electrons. Generic reaction that represents an ionization energy comes down to some generic element X in a gaseous state, which then has an electron removed. That's why electrons on the right side. And then the gaseous ion that comes as a result. What about my energy change? Well, the energy change, again, should be pretty straightforward, too. It's an energy input, right? So in terms of a delta H, right, in terms of my delta H of the system that my atom is involved in, what is required? Well, again, it's going to be a positive delta H because it is an energy input that's involved here. Then what? Well, 2 trends you have to worry about. You have to pay attention to ionization energy of different elements, right? And also the successive ionization energies of a single element. And we'll come back to that in just a minute. One thing I also want to mention, make sure that you understand the ionization energy is kind of a reflection, essentially, of how strongly the protons hold on to their electrons. So definitely effective nuclear charge is involved here. So the higher the effective nuclear charge, the higher the pull is, so the stronger the pull is on those outer electrons. So that means it's going to be a stronger or higher ionization energy, meaning it requires more energy to remove the electrons because they're being held on so tightly by the protons. First of all, let's go and talk about trends. So moving right across the period, how exactly does the effective nuclear charge involved here? And I kind of mentioned that in the previous slide. So moving across the periods, what does effective nuclear charge do? Well, as you go across from left to right, effective nuclear charge increases. So that means the stronger, as you go left to right, that means the nucleus, the protons, are holding onto electrons a lot tighter. That means my effective nuclear charge then causes my ionization energy to also increase, because that means more energy is required to pull away from more tightly bound electrons. Moving down a group, my effective nuclear charge is more or less constant, right? Because it kind of stays the same going down the group. So that ends up not being a factor here. But what you do know is that when you go down a group, I have more and more energy levels, and they get bigger and bigger. Right? So that means you should know that the amount of the actual pull on the protons, the pull of the protons on the electrons, has kind of more or less weakened. Also because the atomic radius has increased significantly. So that means you have a further distance. So considering you have lithium and you have your outermost boundary about here, towards the bottom francium, which is much larger because the protons are holding onto the electrons much less, is going to be there. So if I have electrons out here and electrons out here, the distance between this and this, is smaller. So that means this has a much greater distance. And according to Coulomb's law, if you have a greater distance, the attractive force, right, the denominator, is going to make the overall attractive force smaller. So again, francium will have a very low ionization energy because it requires a lot less energy to take this electron off, because again the protons are so far away and only weakly holding on to your electrons. So there you go. How can you then relate atomic radius? Well, essentially the bigger the atomic radius, the smaller your ionization energy. Okay, and I think that's fairly intuitive, involving an effective nuclear charge with your atomic radius. Now, this is a little diagram here kind of showing you the trend overall. So this is essentially every single element, so your atomic number going from left to right, and then the first ionization energy that's associated with this. Now that means your elements here all kind of have a different sort of a pattern. But overall, again, this is one period right here, it increases. And this is another period right here, it also increases. This is another period right here, it increases. This is another period involving a lot of your transition metals, which you don't really care so much about in this level of chemistry. And overall, again, they increase as well, and it increases. So across the periods, this shows that they increase. Down a group, all right, so this right here is hydrogen. So down the group, group 1, hydrogen, lithium, sodium, potassium, rubidium. That again demonstrates that it is decreasing as you go down the period, go down the group. And you can also see that here with helium, neon, argon, so on and so forth, down my noble gases, it also decreases overall. But again, this is a demonstration of trend, but not necessarily is a perfectly smooth pattern. So this right here, you notice, it kind of has a bit of a dip, even though overall it's increasing. All right, this one also, again, a little dip here. And this happens in several locations, especially with our main group elements. Now, why is that? Well, that's something you have to consider. Let's take a look at this right here. If you remember the degenerate orbitals in oxygen, for the degenerate 2p orbitals anyway, you have 4 electrons that are filled. So you take this right here, up, 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 and then you have the down one that's pairing up in this first one. Compare that to nitrogen. Nitrogen is just an up, and up, and an up. Well, again, compare that to what we have in the previous slide. So let's find oxygen and nitrogen. This right here is our oxygen. Right? And this right here is our nitrogen. So oxygen ends up having a lower ionization energy than nitrogen. Well, again, why is that the case? Well, if you remember from a while back, there's a certain rule that said for any set of degenerate orbitals, if it's half full or if it's completely full, the energetics are favorable and more stable. So this right here, all right, this right now, obviously this one is not completely full or is not halfway full. It's partially full. This one is halfway full. So this right now is stable as is, but this one is not stable. So if you remember the definition of ionization energy, we're trying to remove an electron. Well, what happens if you remove an electron from the oxygen? Well, this one goes away, right? So this one is removed, and so you're left with a half full degenerate orbitals. That's good. That's a favorable thing. So that's why the energy required to remove that electron is lower than nitrogen, where as is, before you remove an electron, is already half full. If we removed one, we would take this one out, and you would end up getting some partially full mess, which does not demonstrate any sort of energetic favorability. So that's why you see nitrogen having a higher ionization energy than oxygen.